we are looking at slightly more complex if loop, where you have also else conditions as well as elif conditions. So here on the left hand side you have got if then else loop, and on the right hand side you have got a loop that is fairly extensive. So it is like if then elif and another elif and then else and then phi. So you have basically 1, 2, 3 and 4 conditions. The fourth one is a negation of the condition 3. So the else is applicable for the previous elif, okay, and therefore you have got 4 different command sets that can be operated on. So let us see this in action and try how does that work. So the example script for the extensive if elif loop is here. So what I'm doing is that if the number of arguments is greater than 2, then I am saying that the number of arguments given is more than sufficient. So I am actually expecting 2. So if you have given more than 2, I say you have got more than 2 arguments. And if the number of arguments is greater than 1, then we are saying the arguments given are sufficient. Okay, so which means that it is processed after the first condition. So naturally it should be only when there are 2 arguments. Okay, and then the third one is greater than 0, which means it should be 1 argument. So I am saying argument was given, 1 was given, but it's not sufficient. And then if you see else, it's applicable to here, which means it is equal to 0. So if the number of arguments is 0, then I am saying that arguments are needed. Okay, so this can be executed by using arguments. So what I will do is I will execute it to display each of these options. So first I will execute it with 3 options. So I will say A, B, C. So there are 3 arguments. So it says that you have got more than sufficient. Then I give it with 2 arguments. If it says arguments are given and sufficient, then I will give 1 argument and it says not sufficient, and then I don't give any argument, it says arguments are needed. So you can see all the 4 segments have been reproduced, and what we are looking at is just number of arguments to go to each of the loops that we are interested in. So you can actually place any other condition for each of those if elif and the further elifs below it as you like, but remember that the logic is going to be checked from the top, and therefore you have to always analyze what is actually being evaluated in the second or third loops, carefully seeing what actually has failed the first condition. Okay, so the if elif loop is quite rich in bash scripts, and you can try that out to test your conditions quite extensively. Now you have learnt perhaps in C or C++ language that if you have many else if conditions, then perhaps you should be using a case statement. So in the case of C language it would be a switch case, and in bash also it's available. So it's called the case Isaac statement, which we have already seen in the previous session. What I want to show you is that within the options that are being matched against the variable, you could also have a pipe to show different combinations that are possible. So in this example that is on the screen, you are seeing that if the variable is matching the first option, then the first set of commands is executed. If it matches the second option or third option, then command set 2 is executed. If it matches either the fourth option, fifth option or sixth option, then command set 3 is executed. And if it does not fall into any of them, then by default the command set 4 will be executed. Okay, so let us try this out using an example. So the example script to test the case is here. So what am I doing? I am asking a question, what is your favorite image processor? And then I am picking up the name of the image processor from the prompt. So I am asking that from the user, and whatever was available, then I am going to compare with the options here. So either a capital G or small g can be there in the first position. So if you are going to give the option GIMP or Inkscape, then I am giving the output as good choice. If I see any string that starts with Adobe, either with a small a or capital A, I am going to say that it costs a lot and needs a cloud. And here if I have an option like image J, then I am saying, are you measuring things on the image, because it's very good for metrics. And for anything else, I am I'm saying that I don't know that such a program could do image stuff. Okay, so let us just run this and see how it is. Remember that the case statement has double semicolons to indicate the end of each of these options, and Isaac is the way that the case is going to end. Okay, so let us try this out. And I'm going to give the first option, so I will give GIMP, and it says good choice. I try it again, small GIMP, it works. And I try it again and give Inkscape, and it's working for the first loop. And then I give Adobe Acrobat, okay, and it gives the second option. There's a star here, if you notice, there's a star here, which means that I can give an option that is slightly longer than what I have listed in the script. And if I give image J, then it is giving the fourth option. Now if I say image J and then I give something else, and you see that I don't match with this because there is no wildcard there. So which means that I have to exactly match the string, and if I did not match, then it will go and fall into the default option, in which I am stating that I did not know the name of the option could do image stuff. So that's what I'm saying here. Okay, I did not know that image J hyphen LKJ STF could do image stuff. Okay, so you see that the use of star, the use of the BRE regular expressions is quite useful in ensuring that the way you are expecting the options to come could be captured as accurately as possible. Okay, so let us look at this case loop again once more. So you have got case, variable name in, after that the options, and then the commands, and then double semicolon, and again an option, command, and double semicolon. Default star, command for the default options, which is fallback options, and then double semicolon, which is optional. The last double semicolon is optional, and then Isaac to close the case loop. Okay, so this is something that is quite useful. As you would guess, at least the early years of the Linux usage, the programmers were all C programmers, because most of the system commands were all C programs, and therefore people wanted also to have some features that are possible as extensions to the POSIX standard to be implemented in bash scripts to mimic some of the loops that they miss, okay, from C language. So for loop is one such beautiful construction of language where you could actually also have that in bash. Remember that is an extension to the POSIX and may not be available in some of the older shells. Okay, so the way it is done is as follows. You have the three conditions exactly the same way that it is working in C language, except that there are no braces to start and close the loop. Instead, you have a do and done to close the loop. Okay, and let us just try this script. There are two such loops that are possible. So you also have the possibility of multiple variables being initiated, multiple increment operations being performed, but you must have a single finish condition. And you could see that this also is very useful feature, because it allows you to have multiple variables vary in a particular sequence. So for example, in this loop, the A is actually increasing and B is decreasing, and then you are printing them both side by side. The finish condition has to be unambiguous, and that's why there's only one finish condition that is allowed. So you could have as many variables that are actually simultaneously changing as you would like. Let us see this in practice. How does it look like? So the C for loop example, the first example is what I have shown you on the slide itself, and let us just run that out, and you see that it is just simply displaying the values of A, and here I am actually using only the power operator. So A to the power 2, okay, A square is being printed. So from 1 until 10, okay, until but not including, because here we are saying less than, okay, and each time A is automatically incremented here in the same way as C language is done. And remember, there is a double parenthesis for the for loop, and here also there is a double parenthesis because there is an arithmetic operation being performed inside. Okay, so this is a very simple and beautiful loop that does exactly what you would have expected in a C language style loop with a similar kind of a construction. So we can do this with two variables. So here what I am doing is I am initializing two variables and incrementing one of them and decrementing the other one. The finish condition is given by only one of the two variables. And what I am doing is that I am squaring the first one and the second one and displaying them side by side. So let us look at the output. So as you could expect, we are going from 1 to 20. So from 1 to 20, okay, but not including 20. So 1 to 19. So 1 to 19, you are having the square that is displayed, but the B is actually going in the reverse direction from 20 to 2, and it is also being squared and displayed. Okay, so this construction where you have got multiple initializations and multiple increments is also sometimes very useful for certain operations. So let us modify this to see how does it work in case you are looking at the variability. So let us check if I can actually use the different variable here. So now because B is actually starting from 20 and coming upwards, so I would actually increase it, and the finish would then should be something a small number, so I would put as 1, and then let us go ahead and try this out. And you see that the same output has come. So you can see that you can have the finish condition for one of the two variables, but it is up to you which one you want to choose. Now there are sometimes requirements that the output of a loop is stored in a file so that it can be processed later. You can always split the script in such a way that you can run the script, redirect the output of the script to a file, and then have another script to look at that file to do further processing. So you can always split the job and do it in segments. But it is elegant if you can also do some of it within the shell, and a very nice feature is available here. So you have the loop that is written exactly like any other loop, but after the end of the loop, if you have a symbol to mention the redirection of the output and a file name is given, then the output of the loop alone is going to be put in that particular file. Okay, and here the file name is given as a temporary file with a dot followed by the process ID, so that there's likely no confusion with other files, and the output can then be stored in the file name. So let us just check how does this look like. So here is the loop output script, and I am doing something little bit more here. So I am having the file name as large file.txt, and I am checking whether such a file exists. So if it exists, what I am doing is that I am refusing to go further, mentioning that it is existing file, so I don't go further, I exit, which means that I don't want to overwrite the file. And if such a file doesn't exist, then I can go on to redirect my output onto that file, and that is what is being done in this loop. And what am I doing? I am actually outputting two values, I and I plus 1. Okay, and how many of them? 10 of them. And do not forget to increment I, because otherwise you will be entering an infinite loop, because I is 1, and while I is less than 10, the loop is running, and you know that unless you increment, you don't reach the end of the loop. Okay, don't forget that. And I am writing two numbers side by side, and when it is done, then it is going to be written to the file name, and after that I am going to state that the file has been written and just check the size of the file. Okay, so let us run this out, and you do not see the output of the echo command of this position coming onto the screen because it is already redirected to the file. Okay, so it has been written, and you can see that the file has been written, and let us just check the output of the large file, and it has the lines that we expected. Now if I run it a second time, what would you expect? You see that because the file name is already existing, so the script would not proceed further and stop. So this is a check that you can actually have for yourself, so that you don't overwrite files if you are not intending to do that. So what I would do now is I will remove that file, and perhaps I will go ahead and edit it, so that instead of 10 numbers, I would actually have, let us say, 10,000 numbers, and then I will run the loop. And I want to also find out how much time it takes to run this loop, so I will put a time command in front of it, time followed by the script, and then you can see that it runs, and for very small time. I mean, it runs less than a second, and you are able to see almost 100 kilobytes of the data has been generated, and it has been put in the large file. WC minus L large file will tell you that there are basically 10,000 lines. It has been done in a jiffy. So you can actually produce numerical output to prepare for some other processing or some testing quite fast using these loop conditions and writing the data to files. And I don't think one can write a file with so much of data in such an elegant fashion as what we have done till now. So look at the script. It is so elegant. You are writing the data to a file in just a couple of lines. Sometimes there are situations where you would like to break out of a loop. Okay, so here is a situation where we have two loops, and we would like to break out of the inner loop if we encounter a number. Here in this case it is number 5. Okay, so we are writing numbers from 0 to 10, and then we are incrementing the I and then checking whether it is equal to 5, and if it has reached 5 then we break. Okay, so it is just to test how do we break out of a loop. The test condition here is silly, but you could actually have any other test condition. Sometimes there are situations where you are doing some file related activities like creating backup files or something, and you may want to have a test condition to check how much free space is available on the disk, and if it is less than say 5%, and you don't want to go further and do any more file generation, and you may want to come out of the loop by a break. Okay, so some such possibilities are there in real life. So you want to come out of a loop using break, and that is entirely possible. So the condition with which the break is going to be applied is here, and let us try that out with an example. So the example of the break condition is here. So we are going from 0 all the way to 10, and when you equal to 5, then we output a string saying 5 is bad news, and we break. So what do you expect to see as an output? So you will go from 0 to 5, and then after that it doesn't go further. Okay, so the way to use the break is that you have a condition to break. So there's a if followed by a condition, and then within the condition you may want to have a message printed before you break, which is useful for debugging later on. Sometimes when you are inside a loop and you want to break not from inner loop but actually from the outer loop also. So if you have n number of loops that are nested, then you may choose to break out of any of those n loops. So a break followed by an integer will tell you up to what level you want to actually traverse upwards and then break. So if you say break 2, it means that it is going to break out of not this loop but one level up, that is this loop. Okay, so you could choose to have that. And here is a situation where what we are doing is we are printing the numbers, and the j value is going horizontally without a break. So you can see printf without a new line, so that's going horizontally. And whenever we finish the j printing up to the value of I, then I is incremented, and then I is printed on the screen. So you see that it is like showing you a triangle of numbers, and we are seeing that whenever the j reaches 7, then we want to come out of that. Okay, so that means up to 6 the triangle is full, but the 7th row at the last digit of 7 to be printed, then we have a problem. We want to come out of that loop, and we want to stop executing completely after that. Okay, so that is what is being done with the break 2 as a condition here. So let us try that out. So here is the loop that we have seen in the slide, and we are actually breaking out, and we also have a echo command which I would like to uncomment now. Okay, and then I will break out of that. Okay, so you see that as soon as the 7 is displayed, then you are coming out of that loop. Okay, and I can also come out of the first loop. And you see that the display is a bit different, because when you come out of the first loop, then the outer loop is still, when I come out of the inner loop, the outer loop is still available, so it is printing up to 9. Okay, so you can see that the way you want to break out of loops can be quite different in different purposes. So here is a number that you should tell whether you want to break out of this loop, then you have to say break 1, this loop, then break 2. Okay, so I have put break 1, which means I am coming out of this loop. There are situations in a loop where you don't want to break, but you don't want to process commands that are below a particular level. Okay, and you want to continue with other iterations. That is, you have a set of commands that are in the loop and you do not want to process some of them if you have reached a particular condition and then want to do the next iteration without any problem. So which means that you would like to actually continue the loop by skipping the remaining commands. So you have the situation here, the continue is used. What it says is that whenever the j value is between 4 and 5, then you don't want to print. Okay, and you can see that here on the output the 4 and 5 are not being printed. Okay, and for other j values this part is not applicable, so it goes on to print those values. So you have seen that 1, 2, 3 is being printed, 6, 7, 8, 9, 10 also are being printed. So the continue is basically telling that do not process the commands that come after it. That means the printf $j is not being processed. Under what circumstances? Basically whenever j value is greater than 3 and less than 6. That is, whenever the j value is taking value of 4 and 5, do not execute the command that follows the loop. That is basically printf $j. So do not print j. Okay, that's what we are telling here. Okay, I is printed with a loop in the front and therefore that is a separate number that we are seeing here. The j is what is printed in a horizontal line after the colon, and j values of 4 and 5 are being skipped. Okay, so you can come out of the loop skipping the commands below it, but continue with the iteration process by using the continue feature. So here is the script that we have seen just now, and we execute that to see that the output is what we have seen on the slide. We will actually now modify that and say that instead of less than 6, I would make it as less than 7. And you see that the output is slightly different. It is now between 3 and 7 that are being skipped, and otherwise remaining ones are being printed. So which means that only one line is being skipped. Okay, only this command is being skipped. Okay, other than that the loop is actually proceeding to continue. So the continue command that way takes effect only for what is below it. There is another keyword called shift. What this does is quite destructive. It would actually shift the arguments by 1 and then reset the positional variables like $1, $2, etc. The values are reset so that you can actually refer to the variables after finishing up the processing of some of the variables. So you can shift through the variables and then process the arguments. But whatever has been shifted to the left are all lost. Exception is $0, and that refers to the name of the script itself, and that will not be touched. Here is one example of the shift command. So what we are doing is that we are running through the list of arguments. So $1 means first argument. We are putting in quotes so that it is treated as a string, and then -n we are asking whether it is a string with non-zero length, and if so, then we go on to print the argument number and the value of that argument. Okay, and we are shifting. Okay, and then we are incrementing I, which means that we are printing 1, 2, 3, 4, etc. as I is incremented, but each time we are shifting the arguments one after other so that we are actually processing all the arguments one after other. Okay, and when we are done with the loop, there will be no argument left because -n will fail when all arguments are processed, and therefore the loop will actually end. Okay, so let us try this out in shell and see how does it work. So here is the example of the shift keyword, and what we are doing is we are initially reporting how many arguments are there. After that we are printing the first argument and then shifting. So when I shift, the second argument will come to the first position, and I want to note down that it's the second argument, so the I variable is incremented by 1 using the arithmetic operation. And how long is this loop going to run? It is going to run until there is no argument available. That means that if all the arguments are gone, then the $1 would have null, and therefore the loop will stop. And after it is over, then I want to also print the number of arguments, and you should see that it should be 0. Okay, so let us try this out. So first, second, third, fourth, and you can see that all the 4 arguments have come. So without using the $2, $3 or $4, I am able to access the second, third and fourth arguments because of the shift operator that is available. But it is only good in case you do not need those arguments any further after the processing, because it's destructive in nature. After the arguments are shifted to the left, then they have gone out. This is also useful in processing unknown number of arguments one after other. So let us look at that as an example. So you can see that all the 26 arguments have been processed one after other, and in the end I have got 0 arguments left. So warning, you can use the shift when you do not need the arguments any further, because after shifting to the left, the arguments are all lost. There is a command called Exec. It has a lot of features with respect to redirection of input output. We are not looking at them now. It is also used to replace the shell with a new program, and that is what we will actually see. And if the new program has been launched successfully, then the control will not be given back to the old shell because it has been replaced. But in case the new program has not been launched, then the control will retain with the shell, and you can go on to do other commands. So usually the exec command is used to launch a different program which would take further action, and the initial shell that has been used to launch it is no longer required. So situations like updating packages and compiling and installing modules, etc., that are done by apt would use a feature something like this, because the shell in which such commands are running are no longer needed once the job is over. So let us try how does this command work, and for that I will use an app called Xterm to try how to launch an app from the bash shell. Example, here I am showing the process ID of the shell, and then I am launching an Xterm, and then I am seeing whether the Xterm would show me the process ID which is same or different from the parent bash shell. So first of all, let me see what is the bash shell I am running. It is 2360. Now I will execute this script. So now I have got the Xterm that is available, and when I am launching it, you see that the program exec example was running with a process ID of 12073, and then it has launched the Xterm. Now Xterm would also have its own process ID, and you see that it is 12102. And I see whether this parent shell 12073 is available, and you see that it is showing as Xterm. Okay, and it says that it has been launched by 2360, which is a bash. So you see that it is actually looking as if from the bash I have directly launched Xterm, but actually what we have done is from the bash we have launched the script exec example, and then it is a script which has launched the Xterm. But however, it shows as if the parent shell for Xterm is 2360, which means that it is an exec example process which actually got replaced by Xterm. So you see that we are back to the parent shell with the PID 2360. And you could use the exec whenever you do not need the original script or shell that is launching it. And it's a good idea to also have a comment to be displayed in case the launching has not been successful. So that's what we are doing here. In case the Xterm was not available, so it would give a message. Now I will intentionally change the spelling so that I don't have this successfully running. So which Xterm 1? So there is nothing called like Xterm 1 is not there, so it should fail. So you see that the failure has happened